Yeah. So our first speaker today is Lars Andersson from Twistor. He will talk about stability of spacetimes with supersymmetric compactifications.
Okay, thanks. So thanks to the organizers for inviting me and so on. And I guess I should probably apologize if there's some of you who have heard this talk before, because I seem to have given this a number of times. This is actually work from a few years back. And the one reason I'm talking about this now is that I want to come back to, I'm planning to come back to this problem this fall and try to prove the conjecture that will be made later on. And so the talk is about, basically, I was talking with Bernardo, so this sort of originates in some old work by Witten from the, I guess, the 1980s, where he was pointing out that if you have a Kaluza-Klein solution, or if you have sort of Kaluza-Klein initial data, which would be, for example, R3 cross S1, this is semi-classically unstable in the sense that there's another solution of the Einstein constraint equations, which is actually static and dynamically unstable, at least in harmonic gauge, and that is the Cauchy data set that you get for a 5-dimensional solution of Einstein equation by taking Euclidean Schwarzschild. So Euclidean Schwarzschild looks like R3 cross S1 near infinity, but it has, if you look in harmonic gauge, it has a negative, the perturbation operator has a negative eigenvalue. So it's, at least in harmonic gauge, this solution, this Cauchy data set is dynamically unstable. So there will be exponentially growing modes in harmonic gauge. So what does that mean? Does that actually mean that this Cauchy data set is dynamically unstable in some gauge invariant sense? This is unclear to me. And so this came up, there were many papers talking about the action for gravitational instantons around that time. And this dynamical instability is related to the fact that the Lechneritz Laplacian on non-hyperkähler instantons typically has a negative eigenvalue. So this is not known in general, but it's known for all examples of non-hyperkähler instantons that we have. So Kerr, Taubolt, and Chen-Teo. The general picture is not clear at this time, because we conjecture that those are all examples, but that's far from being proven. And this is also this whole story is also was actually sort of prompted by statements by Roger Penrose, and in his, you could say, in his campaign against string theory, because these type of Cauchy data sets with compact dimensions was proposed in the 1980s as a mechanism for the emergence of the physical space-time from higher dimensional supergravity string theory situations. And so, as Witten pointed out, there is a semi-classical instability. Roger was arguing that there is actually a classical instability. And what we show here is that this, at least for if the background Minkowski is has high enough dimension, this claim is not correct. So there were there's some amount of hand waving in those arguments that didn't pan out. So let me start. I'll come back to this. So we're talking, I guess, nonlinear. Okay, so we're talking about Einstein gravity. This is sort of motivated by supergravity considerations, but this talk is only about classical gravity. So we have the usual setup. We have some Cauchy data set and so on. And this is, well, I don't have to say this here. So this is part of the standard model. And it's viewed as sometimes as a low energy limit of string theory or supergravity. As a PD system, this Einstein equation itself is degenerate due to the general covariance. So it doesn't have a particular type. But to study this from a PD point of view, you have to introduce a gauge condition to kill off this degeneracy. And so one example is the wave gauge. So here G hat is some background metric. And this expression here is basically the tension field of the identity map from the space-time with the G metric, space-time with the G hat metric. So this is a covariant, this is actually a vector field. So it's a covariant expression. There is no coordinate choice. There's a lot of confusion about coordinate choice when you talk about gauge. And so if you write down the Einstein equation with canceling all terms that are zero due to this condition, you end up with a wave equation, which has this form. So here this S is some nonlinearity, which is quadratic in first derivatives. and then, I mean, so Gerok and Choquebrihar showed that the Cauchy problem for the Einstein equation has a unique maximal development. So there's given a Cauchy data set solving that constraint equation I had on the previous slide. There's a unique maximal global hyperbolic space-time that solves the Einstein equation, and that has this Cauchy data set isometrically embedded in it. And so, of course, the simplest example is Minkowski space. And this has this sort of conformal diagram where you have, in the outgoing null directions, you have a conformal boundary to the future and to the past. So we can think of sort of scattering from past infinity to future infinity and so on. And Minkowski space is known to be dynamically stable. And the hard part here is when you're in dimension 4. And this is due to the fact that you have this quadratic self-interaction, and in dimension 4, quadratic self-interactions are difficult due to the fact that the field decays as you go out in null and time-like directions slowly enough that these quadratic self-interactions in general would cause a blow-up. But due to some cancellations in the Einstein equation, so-called null condition, this doesn't happen. So this is what they were able to show. And this was like the big important result in the sense that this brought PD people into the field, so to speak. So this was an important application of PD theory to geometry. And later on, it was proved. So this used some kind of double null gauge Later on, stability in wave gauge was proven. This is more difficult because the straightforward null condition doesn't hold. So there's a kind of weak null condition. Yeah, so this slide is just to put this in a kind of perspective. So Minkowski space is a kind of trivial steady state which has maximal symmetry. But there are interesting steady states which have where the symmetry is broken. And so typically this happens whenever you have Einstein coupled to other matter fields. So for example, fluid, those are stars. Einstein-Vlasov, for example, galaxies. Einstein-Klein-Gordon. So there's a Klein-Gordon geon, or also called Kaup soliton, and this relates to sort of hairy black holes and what they call mini boson stars, which are dark matter candidates. There's the famous Bortnick-McKinnon soliton in Einstein-Yang-Mills. You have Einstein-Dirac, and you also have many solitons in the absence of gravity. So there's a huge amount of such non-trivial solutions which are actually steady states, and their dynamics is a very interesting problem in its own. So this is this is somewhat of an aside, so to speak. But and of course the very famous instance of a non-trivial steady state is the Kerr black hole, which is a solution of the vacuum equations. It's stationary and axisymmetric, but it breaks symmetries of Minkowski space down to a two-dimensional set of killing fields. But there's special geometry, so there are kind of hidden symmetries, so second-order symmetries and so on. And that's what allows you to handle, allows you to understand the Kerr black hole and its dynamics. And there's the famous black hole stability conjecture, which says that the sub-extreme Kerr is dynamically stable. So sub-extreme is when you have a non-degenerate black hole horizon. Some of the features of this phenomenon is that you have rotation, so this means that you have superradiance. You can send in waves that come out with higher amplitude. There's the Sapolsky-Munster equation, which allows you, which is the key fact that allows you to understand this stability. That's a confluent Hoyne equation. So this is just basically sort of to give some context. This stability is essential to the validity of the Kerr black hole as a physical model. And this means that if it would turn out, which we still don't know, that the Kerr black hole, that rapidly rotating Kerr black holes are dynamically unstable, they would not be able to form in nature, so to speak. And therefore, you would have to revise basically the whole interpretation of what you observe about galaxies and so on, because galaxies are believed to be to have, most of them are, it is believed that most galaxies contain a supermassive black hole at the center, and this supermassive black hole plays an important role in sort of organizing the life of galaxies, so to speak. So that's why this stability is so important. It's not just a mathematical problem; it's an astrophysics problem. Well, that's conceivable. Yeah, that's you could have sort of long-lived, but not actually steady states. So you could have long-lived configurations that are not actually steady, but are, as you're saying, are unstable on a very long time scale. Those would be, you would have a hard time distinguishing those from actual steady state. But of course, I mean, this stability of Kerr has been conjectured for more than half a century, and it's now partly proven, as I mentioned. But the full picture is not yet known. So this is somehow a little bit of background to what I'm going to talk about later, because what I'm talking about is the question of stability of some solutions which have been viewed as essential in the string theory supergravity scenarios. So the black hole stability, there's been a lot of recent work on that, and a few years ago, Kleineman and collaborators proved that for very slowly rotating Kerr black holes, nonlinear stability holds. And this made use of this idea of that you can use the second order symmetry, the Carter symmetry operator, to prove dispersive estimates. So this was a big breakthrough, but the full story is far from known. Okay, right. Okay, so this was a little bit of background, and now this here I'm mentioning the paper of Witten from 1981 that I alluded to in the beginning, and so in the 1980s there was this picture of how physical space-time emerges from the 11 or the basically higher dimensional space-times that come up in supergravity and string theory, and the idea is that you have the space-time that you actually see is something like four-dimensional space-time cross and a compact space, for example, a Calabi-Yau. So that was this scenario was the reason why Calabi-Yaus became so important. And this, as you know, this came about at a time when only a very few Calabi-Yaus were known, and so it was believed to be, have some physical information in the fact that you have so few Calabi-Yaus. But then, sadly, there are now many Calabi-Yaus, so this doesn't have so much. Maybe there's less information contained in that statement. And so those are analogs of this Kaluta-Klein vacuum that Witten was talking about in his paper. So Kaluta-Klein would be like four-dimensional Minkowski cross a circle. And what Witten pointed out is that this configuration is semi-classically unstable in the sense that there's a space-time that has the same asymptotic behavior at infinity, but which is dynamically unstable. So that's what he referred to as you could tunnel to this. You could tunnel to this other state, but and so this means that you would not expect this. You would not expect this to form in a sort of quantum gravity type scenario. But he also pointed out in this paper, as an aside, that that this space-time is actually classically stable. So if you just make small perturbations of this space-time, then it's you would expect these perturbed solutions to actually decay to a configuration like M4 cross to a Kaluza-Klein configuration. And this was just stated as an aside, so to speak. So what really motivated our interest in this were these statements by Roger Penrose, who argued that if you have a space-time which contains a compact minimal, well, so he had some result that said if you have a space-time with a compact minimal surface, then you have incomplete causal geodesics. And then he was arguing that this is somehow a stable statement, so that if you have a compact factor like you have in Minkowski cross a Calabi-Yau, across a compact Calabi-Yau, then you cannot avoid having collapse and the collapse will happen on a time scale that's comparable to the size of this Calabi-Yau. And in the string theory sort of supergravity scenario, the idea is that this Calabi-Yau is very, very small. And this means that you would expect to have this collapse on a very, very short time scale. And so this would mean that this would prevent such space-times from emerging through some dynamical process. Some theorems in this direction were proven, but with additional curvature assumptions. So, for example, this is a paper by Greg Galloway and Sinovia. Which Penrose? Well, I think he was thinking about ordinary Einstein equations, so not supergravity.
But here you said now, here he assumes no convergence. You know,
Yeah, something like that, right? Yeah. But anyway, I mean, so the point here is that these, so there were some arguments here that are simply not fully worked out, and he also, so Penrose had considered one situation where you have essentially that the whole initial data set is sort of is set up so that you're actually sort of, it's collapsing not just locally, but the entire scale is collapsing. And then of course you can have this situation. But if you but in other statements he was arguing that for some basically dimension, well, for some reasons related to his results on singularity theorems, that you could prove this in some generality, but that turns out to be not correct, and that's what this talk was motivated by. And so this raises the question, you know, are these compact if you have a supersymmetric compact dimension or a space-time with a supersymmetric compact factor, is that classically stable? And so in the paper I'm talking about, we show that if the Minkowski factor has sufficiently high dimension, and you have a compact factor which is has special holonomy, for example, a Calabi-Yau, then these are globally nonlinearly stable in the context of vacuum action gravity. And the condition is that this compact internal space has a cover that admits a parallel spinner, so in particular special holonomy. And so this contradicts what Penrose was expecting to be true, but at least for if this Minkowski factor has sufficiently high dimension, but it's still compatible with semi-classical instability in the sense that Witten was talking about, because, and I don't actually know what the story is there. I mean, so in 4 dimensions, you can tunnel from Euclidean space across a circle to 4-dimensional Euclidean Schwarzschild, which is unstable. But what's the situation if you have, let's say, 3-dimensional Euclidean space cross Calabi-Yau? Is the same thing? Can the same thing happen? I don't know what if this has been sorted out actually. But anyway, yeah. I'm not sure. I think that because in the situation we're thinking about, maybe it is related. I don't know, but in the situation we're thinking about, if you look sort of near infinity, the space-time looks like a product of Minkowski cross the Calabi-Yau, and near infinity, or asymptotically at least, the moduli degrees of freedom are not excited. So I'm not sure if maybe we can talk later because I'm not sure exactly what this modular stabilization refers to. Okay. Yeah. So this is so the result here is so there is a kind of proof of principle, because we're assuming that the Minkowski dimension is high enough for simplicity. And the reason this makes life simple is that the higher dimension of the Minkowski space, the more room there is for the wave to spread out. And this means that the waves will fall off faster than in a low dimensional space-time. And this fast fall off means that the nonlinearities are easier to handle. But we conjecture that stability holds for when the physical dimension is 4 also. But this is more difficult, and actually you need to exploit the null structure of the Einstein equations. No. So I think we need like D equals 9 or 10, something like that. So because yeah.
I mean, Witten's aside was presumably concerning linear stability.
Yes.
Has that been proved for the simple case of D4 plus?
Yeah, I'll come to that. That has actually been proven now recently. Yeah. Yeah. So I'll mention this. So this was Zoe, actually, Zoe Wyatt, who is in Cambridge, but not, I think, not at the moment. So our collaborator has proven that with some other collaborators. So anyway, so we conjecture that the stability holds in the physical dimension. And this is what we're planning to work on this fall. And as I've been saying, so this, and so this question was actually raised by Yao to me some more than 10 years ago. And he was saying that if this doesn't hold, then this is like a disaster for supergravity and so on. And this stability, but if this stability fails to hold, this would be like a disaster in a certain sense. But in fact, it does, as we're arguing, it does hold. And also, as an aside, so there's a positive mass theorem for such SUSY, supersymmetric compactified spaces. So this is the paper. So there's this from 1 year ago, basically. Kuno, Stingo, and Zoe Wyatt proved that nonlinear stability for this four-dimensional Minkowski cross S1 does hold. And so that made important use of the fact that S1 has no curvature, so to speak. And this is so this does not generalize in any straightforward way to the case where the compact factor is a higher dimensional Calabi-Yau. And so there is some important sort of parallel between this situation with the supersymmetric internal space and the Kerr black hole, in the sense that in the Kerr black hole you have only two, you don't have the full set of symmetries. You have only two killing fields. And to actually do analysis, you need to use the hidden symmetry or the higher order symmetry related to the Carter constant. Here, the Calabi-Yaus typically don't have any killing fields. So, and you need to do analysis, you need symmetries. So in this case, the rescue is that you can use the Laplacian of this compact factor as another symmetry operator. And so if you look at the linearized Einstein equation, you end up with this, in wave gauge, you end up with this this operator, which is the box, and then you have the Leschner's Laplacian on the compact factor. And this second order, this Leschner's Laplacian, is then a symmetry operator for the linearized gravity. So you can use that to build up a kind of generalized vector fields method to do estimates. Yeah. This one, yeah. But so that acts sort of component-wise actually on this on the metric, yeah, when you're in wave gauge. Well, because it commutes with so this is the linearized operator. So that commutes with this. And so in that sense, it's a symmetry operator. Yeah, exactly. Yeah. So what you get is, so you have the zero modes, which correspond to moduli degrees of freedom. And then you have basically an infinite sort of number of massive modes. So in this linearized picture, if you do separation of variables, so to speak, you have an infinite number of sort of Klein-Gordon equations that are, in the linear situation decoupled, but when you turn on nonlinear gravity, they become coupled, and the masses go to infinity. So it's and Einstein Klein-Gordon stability of Minkowski space for Einstein Klein-Gordon was solved, some years ago, but that was a big challenge. And here you have this kind of infinite number of Klein-Gordon fields basically being coupled. The massless modes. Well, I mean, for a single mode, yeah. So it's not so obvious. Exactly. So in this situation, it's not so obvious. Okay. And so very important fact is that due to the special holonomy, this Leschner's Laplacian on the Calabi-Yau or on this special holonomy compact factor has non-negative spectrum. So there's an inequality like this. And this was proven by Dai, Wang, and Wei. And the reason this holds is that you can write the Leschner's Laplacian as a square. So that's where the supersymmetry sort of comes in. So you build an operator from, basically you apply the Dirac operator to a kind of one form valued spinner that you build out of a parallel spinner on the Calabi-Yau or SUSY factor. And then you can check that this Laplacian is the square of that operator. So it's very, very elegant argument. And so this stability property means that you have essentially mode stability for linearized gravity on these supersymmetric backgrounds. And it's still open whether or not this stability in this sense holds for all compact Ricci-flat manifolds. And this is related to the question of if there are any compact Ricci-flat manifolds that do not have special holonomy. And that's still open. So all known examples do have this stability property. And so here's the main theorem. And so there's this quantity is a kind of measure of deviation from the background. We have to assume that the Minkowski dimension is bigger than 10. And then if the smallness condition holds, then the maximal evolution of the Cauchy data is geodesically complete and asymptotic to this background space as time goes to infinity. And here the high dimension is a simplifying assumption because we wanted to use just some kind of straightforward arguments just to see that things work. And we also assume that the data is exactly Schwarzschild near infinity. So that's another technical assumption. And as I was talking about just a minute ago, so there's this infinite tower of Klein-Gordon-like modes. And so I think this kind of thing has been studied in the string theory literature. But it's difficult to make use of this directly because it's an infinite number. And so this is just saying something about the behavior of waves, massless waves versus Klein-Gordon waves. And if you look at, due to basically the Hummel principle, so in Minkowski space, massless waves travel out along null directions. And if you think about the growth of the light cone, you can and you think about energy conservation, you realize that the wave has to fall off in this manner. So basically, so here in this region, T is like R, and the wave has to fall off like T to the minus 1 in 4 dimensions. For the Klein-Gordon, this principle doesn't hold, so you have a tail in the entire interior of the light cone. Then if you think about the growth of these slices here, you realize that you actually have a little bit faster fall off. It's like T to the minus 3/2 in 4 dimensions. But in this case, if you apply good derivatives in the outgoing null direction and tangent to the light cone, you get faster fall off. But for the Klein-Gordon, that doesn't hold. So there's, even though apparently this looks better, it's actually a lot more difficult to handle the massive field. And in particular, the presence of the mass breaks the scale invariance. So for the wave, you have dilations, which are symmetry operators that take solutions to solutions, but dilations are not symmetries of the Klein-Gordon equation. So that's a big disadvantage when doing analysis. So as just to remind you that when you to analyze waves or wave equations like Klein-Gordon, what you end up using are energy methods. So you can, from the field equation, you can get the conservation law, and this gives you an energy that's conserved of this form. And so you start using this and you commute through the equation with derivatives, and then you get higher order energies that you then try to control, and you try to show that these fall off as time goes on. And so here's an example of what you can do. So those are the type of techniques that you're left with, so to speak, that you're forced to use when working with wave equations. That's basically either such ideas or working on the Fourier side, which is not so easy for nonlinear equations. That's what you can do. Yeah, so here's an important point. So if we look at this equation in 4 dimensions, so here we have Vox equals a square of one time derivative. That looks innocuous, but if you try to apply energy techniques and so on, what you end up finding is that the energy that you want to control, you get an estimate that has a logarithmic time growth. So this signals that there is a problem with this simple looking equation. And in fact, you can have arbitrarily small initial data that will blow up in finite time. And so this tells you that not all nonlinear wave equations are good. You need some more structure in order to have to avoid blow up. And this kind of structure is referred to as null structure. And an example of an equation with null structure is this equation, which has, for example, here the Q could be the space-time, the Minkowski metric. So whenever this quadratic form kills off null directions, then you have a null structure, and then the trivial solution is stable. So so that's so and the important point about the Einstein equations is that there are structures like this, but you have to work to find them. And in particular, in wave gauge, the Einstein equation does not satisfy a null condition, but it satisfies something analogous called the weak null condition that you can then use. Right, and so in higher dimensions, so the reason we did this in higher dimensions is that we wanted to, we just wanted to see that something works. So if you're in 5 dimensions, for example, and you consider this equation in 5 dimensions, then everything is fine, because you then have you have enough decay for the fundamental solution that you avoid. So this log term comes from basically integrating something that falls off like 1 over t. And so in higher dimensions, the Green's function falls off not like 1 over t, but like 1 over t to some higher power, and then you avoid this problem. So this is really 4 dimensions is in some sense critical for, or is the difficult case when you have a quadratic nonlinear action, which you have in most field theories. Okay, and so here, so I told you we need. So we have the Poincare symmetries on the base. We have this additional symmetry operator on this supersymmetric factor. We have to use energy techniques, so for the Einstein equation, it's so I mentioned this already, so I'm just going to skip this. Now, there was a lot of work on the nonlinear Klein-Gordon equations, for example, by Hermander, and so what we're looking at is effectively a quasi-linear system. So quasi-linear means that you have the leading order term is linear in the highest order derivative term. So, for example, the Einstein equation in wave gauge has this property. Yeah, so we have the coupling of the wave system and the Klein-Gordon system. So, and that's the most difficult situation. And due to the nonlinearity, you cannot treat the wave and the Klein-Gordon pieces separately. And in this higher dimensional situation, it's enough to use this hyperboloid method, which basically relies on studying the relation between hyperboloidal time and the Minkowski time. And so you end up with estimates like this, just due to the geometry, so to speak. And you have if you have initial data, which is compactly supported, due to finite speed of propagation, you're staying in a region like in this picture, and there you can prove this relation between the Minkowski time and the hyperboloidal time. And so this is what we end up using in our estimates. And well, so I'm not going to spend any time on the details here, but you end up with controlling due to energy estimates, you end up having a criterion like this in order for the estimates to close. And this is where this condition on the dimension of the Minkowski factor comes in. So we end up needing, with these kind of simple-minded techniques, we end up needing the space-time dimension at least 10. Right. That's right. Yeah. Yeah. That's right. Yeah. So this energy in the hyperbolic time has a certain decay property, and then you can compare that to the energy in the Minkowski time, and you can due to this finite speed of propagation, you can convert this decay from the hyperboloidal time to the Minkowski time and get enough if you're in high enough dimension. Okay, so some concluding remarks. So we have proven this stability for high enough dimension of the Minkowski factor. So this somehow contradicts at least some expectation of Penrose in this context. It's known that this stability holds if the compact factor is just S1, so has no curvature. But we conjecture that not only that, we can actually conjecture that this the stability should hold true, for example, in the n equals 1, d equals 11 supergravity with a compact internal space and a Minkowski base. So, for example, if you take like a G2 space or what is it? You have the 6-dimensional Calabi-Yau across a circle, so you have some 7-dimensional factor. This will be a stable configuration for the supergravity theory. And related to this, what one should do is also to develop a sort of calculus of variation along the lines of what Lee and Wald did, or Ear and Wald, for supersymmetric actions. I think some of this has been done already, but I think not for this, for the interesting case, so to speak. For some special lower dimensional supersymmetric theories, this has been done. And this what they did leads to a systematic analysis of conserved charges, nether charges, and stuff like that. And there's also a positive mass theorem for this theory, but this should be developed in this context where you have a Minkowski cross compact Calabi-Yau, for example. There is, for ordinary Einstein gravity, Dye proved a positive mass theorem in this particular context, but this should be, of course, done in terms of supergravity. Right, and also you can ask yourself, is there a semi-classical instability of supergravity in the same sense that Witten was talking about? I don't know what has been done in that direction. Yeah. Well, I mean, so just from this classical point of view, the supersymmetry, the presence of this parallel spinner is what allows you to write the Lechner-Laplacian, which is the linearized Einstein Ricci in wave gauge. It allows you to write that as the square of a Dirac operator. And the Dirac operator is acting. Yeah. Yeah. Oh yes. Yeah. It's the supersymmetry of the background, so to speak. It's not the supersymmetry of the field theory. But the kind of bosonic, there is some work on the sort of what you call bosonic sector of supergravity, but without the gravity part. So this is just some theory with some form fields and stuff like that. And so that has been proven to have some null structure. So so what's important for the field theory is really the structural properties of the equation. So like null structure and so on. So and I think that originates to some extent from the fact that the action is supersymmetric. But I'm just sort of speculating. I don't know that for a fact. So the Einstein.
I'm told with that supersymmetry, the supersymmetry is certainly driving that positivity.
Yeah, but it's, I think there could also, I mean, so the observation is that if you take you throw out the gravity, but you take just the bosonic sort of form fields and so on from the supergravity, that's a field theory on its own, and that does have good sort of null condition properties. So there's both this kind of positivity that you're talking about that's coming from the supersymmetry, but there's also structural properties like null condition that cancels bad in self-interactions. And both of those properties are essential for this nonlinear stability I'm talking about to hold, right? Oh, of course.
Yeah, very long.
Sorry?
There's something very long.
Yes, yes.
It's all about null. convergence and the incompleteness that you can't get to the future, you know,
Yeah.
you really.
But at least, I mean, so he had, as I said, so he has one situation that he considers where he's essentially having like the whole scale of the entire space-time is sort of collapsing. And so that's not what we're talking about. We're talking about if. Right, and what we're saying is that this does not happen. Yeah, and then there's exactly, yeah. So yeah, so basically in the Planck time or whatever, you would so the universe would cease to exist basically, which would be quite unpleasant, I think. But
I could quite see this. Probably could be a way around what I'm talking.
Yeah, but there was some like hand wavy dimension counting argument, and yeah. And when I looked at his writings on this topic, I sort of momentarily thought I saw, you know, where the flaw is, but at the moment, right now, I cannot put my finger on it. But so we can just present this counter result, so to speak, and say that there has to be something somewhere. There is something missing in his argument on this point. Right. So indeed, this is optimistic, but there's some work relating to the bosonic supergravity field theory, or the one sort of where the gravity is turned off, that is going in this direction. So I'm pretty confident that this is true, actually. Of course, I have no estimate on how difficult it would be to actually carry this out. Okay, so that's all I have to say. So thank you very much. Yeah. You mean unstable in the sense where you don't have the stability property of the supersymmetric? Yeah. Not really. I mean, so one thing that we know is that if you because the problem is that in order for this to get started, you need basically a solution of the background should be a solution of the vacuum Einstein equation. So if you think about Minkowski cross some compact factor, the compact factor has to be Ricci flat, and all known examples of Ricci flat compact spaces are have special holonomy, so they're already stable. So the only kind of non-stable examples that we know are like, you know, Euclidean Schwarzschild and things like that, which are non-compact. So it's I don't really have any good comment on that. You could consider the same problem with a non-compact factor, like, you know, Minkowski cross some instanton, for example, that, or you could consider initial data built from gravitational instantons, which are not hyperkähler. And so that's something that, you know, people have talked about. And what happens in those cases, it's unclear. You could imagine that the dynamics will tend to wash away or collapse or hide these topological or hide these features of the geometry that makes it unstable. But I really no clear view on that.
We'll move on with the questions. 25 minutes, and we have to be back.
Sure.
Still works, so I think there's still hope to serve that.
Okay.